So thank you everyone for coming to my talk. Please feel free to ask questions during the talk. So I'm going to tell you about this work that we put out recently with these co-authors. So we're talking about quantum many-body topologies. So what do I mean by this? So you have some quantum many-body system, some quantum system with infinitely many degrees of freedom and a thermodynamic limit. Let's assume that it's gaps. So the ground state has a non-zero gap between the ground state and all the excited states. So then at low temperatures, you basically just have the ground state. So there's no non-trivial excitation dynamics going on in the system at low temperatures. But nevertheless, the ground state itself can still have some non-trivial structure. And that's what we call a quantum many-body topology or topological order. So you can have topological phases of matter, but they're characterized by the fact that they have non-trivial many-body quantum entanglement in the ground state. And this has many physical consequences, such as quantized responses. For example, we have quantum Hall effect of quantized Hall conductances. You can have fractional excitations, like in the fractional quantum Hall effect, etc. And so when we talk about topological phases of matter, often it's very important to think about the role of the symmetries of a system, because although you can have distinct topological phases, even without symmetry, if you impose a symmetry on the system, then it can get you to a richer classification of topological phases. So for example, a trivial phase can get split up by, once imposing the symmetry, it splits up into different symmetry-protected topological phases. So these are things such as topological insulators, which are protected by time reversal symmetry. And also the non-trivial topological phases can also be enriched by the symmetry, and you get different phases, which would be the same phase without symmetry, but you impose the symmetry that they are sharply distinct phases. For example, spin liquids, they're enriched by a spin rotation symmetry, and you can have different spin liquids, which are distinguished by, for example, quantum numbers of excitations under this free symmetry. So there are many symmetries that appear frequently, like time reversal symmetry, spin rotation symmetry, charge conservation, U1 symmetry. But one important class of system occurs in crystalline systems. So we have some solid, it forms some crystal structure, and this crystal has a space group symmetry. So that includes things like the discrete translation symmetry, some discrete rotational symmetry, reflections, etc. And so actually there's a general classification of topological phases in the presence of space group symmetries, which for interacting many-body systems was developed mainly by me and Ryan Fongren here, and then it's also a group as well, made contributions as well. But in this talk, I want to go beyond this, and I want to talk about quasi-crystals. So quasi-crystals are a different kind of solid state material.
Can I interrupt you to a very, very basic question? I'm sorry, I'm not an expert on topological phases of matter, but you're talking about a many-body topological phase. And
yes.
But you can have systems that have topological phases also for single particle physics. So how do you combine, or how do you bridge the both things, or is it the same?
Well, there is a connection because so as you say, you have normally we can think about it in terms of say it's a fermionic system with no interaction, so it's a free fermion system. And so in free fermion systems, you have bands, and then assuming that you completely fill some number of bands, and you have a ground state that has a gap, a many-body gap. So then you can switch on interactions, and then so what you'll find is that some of the topological phases in free fermion systems remain robust when you switch on the interactions. Some of them are not robust, and actually switching on the interactions will trivialize the phase. And you can also get new phases of matter which are intrinsically interacting, which could never occur in a free fermion system. Does that answer the question?
Yep. Thank you.
So quasicrystals are these new kinds of materials. And so you can diagnose the fact that you have a quasicrystal if you, one way to think about it is in terms of a Fourier transform. So you take a Fourier transform of some local observable, say it's for density or something. You'll see that it has sharp peaks. The Fourier transform contains sharp peaks for a quasicrystal. And so a crystal also has sharp peaks in the Fourier transform because of the lattice periodicity. But a quasicrystal is different from a crystal in the sense that it doesn't have the lattice translation symmetry that a crystal has. And then another way to see that quasicrystal is not a crystal is it can actually have a point group symmetry that would not be allowed in a crystal. So here you see from this Fourier transform that the system looks like it has an 8-fold rotation symmetry. There's no crystal that has an 8-fold rotation symmetry. And so this, I guess, was kind of how quasicrystals were discovered. In the, people looked at X-ray diffraction spectrum, which is basically probing Fourier transform, and then saw that like there was point group symmetries that should not be allowed in a crystal. So that was a discovery of quasicrystals. So that's but then you can also have a real space picture of quasicrystals, which helps you to understand how such a Fourier transform would arise. And so the way you think about it, one way to think about it in terms of these tile pictures. So you make a quasicrystal by taking some fundamental tiles and you fill space with these tiles, but in a way that's not periodic like this. So this structure, you can see there are some patterns, local patterns that repeat, like for example, this star repeats many times, but there's no exact periodicity. There's no translation vector that you can write down such that you translate the crystal by that vector and it remains the same. So this tiling is actually what I use to generate this Fourier transform. So indeed, this tiling will give you rise to a Fourier transform like this. Now, of course, a real material is maybe not literally made up of tiles, it's made up of some atoms, but at least these real space pictures in terms of tiles are helpful to think about the basic structure of a quasicrystal. And so this particular tiling is something that well, people call it the Amman-Binka tiling. You might be more familiar with its more famous cousin, the Penrose tiling. But here in this talk, I'm going to focus on the Amman-Binka tiling well, there are some technical reasons why it's better for what I want to do. Okay, so the question is, can quasi-crystallinity protect topological phases of matter? And so what I want to show you is the answer is yes. But maybe that answer might be a bit surprising. So for example, crystals have an exact lattice translation symmetry, as I mentioned. So some unit cell, and you translate by one unit cell, you get back to the exact same state. And this translation symmetry can protect topological phases. And so an example of that is something like a weak topological insulator. So this is where you take a two-dimensional topological insulator, and then you stack it. You make a stack of these things in 3 dimensions. And then you impose translation symmetry in the direction along which you're stacking. So what it turns out is that this actually describes a non-trivial 3-dimensional topological phase of matter protected by translation symmetry. So if you impose translational symmetry, then there's no way to trivialize a state that you've constructed in this way. And so you can add here in this picture they're completely uncoupled, but you can add terms to the Hamiltonian to couple them. As long as you retain the translation symmetry, it stays a non-trivial phase of matter, and you can only get rid of this non-trivial entanglement by going through a phase transition, and also this gapless surface states that are protected by translation symmetry. So this is the idea of a weak topological phase, for example, weak topological insulator. Okay, but quasicrystals do not have lattice translation symmetry, as I already mentioned. So you might think that therefore, if there's no symmetry, suddenly no symmetry can't protect a topological phase. But what I want to convince you of today is that actually quasicrystals do have analogues of weak topological phases. In fact, I even have a richer classification of these things than occurs in the crystalline case. That's despite the fact that they don't have an actual lattice translation symmetry. But there is some kind of spatial structure, and that's the reason why there's something non-trivial going on. So here I've shown, this is the same as the Amman-Binka tiling that I showed before, but I made a bigger version of it now. So as I mentioned, there's no exact lattice translation symmetry. There's no translation vector that you can write down that, where you translate and you get back to the same state. But there is some kind of approximate translation symmetry that going on here. So to illustrate this, I'm going to show that this translation vector is kind of an approximate translation symmetry in some sense. So this white arrow is a translation vector. So to illustrate this, I'm going to take this quasicrystal, I'm going to translate it by this translation vector. And then I'm going to make it partially transparent so you can compare the translated version to the untranslated version and see if they're different. So here goes. I don't know how smooth this animation is for what you're seeing, because it's, in any case, so this is the translated version of a quasi-crystal. So now I make it transparent, and now you can see where the translated version differs from the original untranslated version. So you can see that there are actually pretty large regions where it's exactly the same after translation as it was before, but nevertheless there are some mismatches. So here, if you see where my cursor is, for example, that's where you see that there's some mismatch between the translated version and the untranslated version. But nevertheless, these mismatched regions are kind of somewhat diffuse. There's pretty large regions where there's no mismatches. And what you can show is that there's actually a sequence of these vectors, arrows getting larger and larger, such that these mismatched regions become more and more diffuse. So in some kind of asymptotic sense, you have a translation symmetry, although for any finite vector, it's not an exact symmetry. So this structure, I'm going to call it a translation quasi-symmetry. It's not a translation symmetry, it's not an exact symmetry at all. So I'm going to call this structure a quasi-symmetry.
By quasi-symmetry,
yes.
You said these spots get more and more diffuse. Can you elaborate on that, or what does that exactly mean?
Well, another way to say it would be the size of these regions that have no mismatches get larger and larger.
Okay, thanks.
Could I ask you, if you did this only with density waves, you didn't do this discrete version, you just sort of, let's say, summed up 8 density waves on that star. Would these regions where they're mismatched go away? Would they be eliminated?
You mean the case where you just take like 2 density waves?
Basically, yeah, that's right. Yeah, so what I would like to do is to take 8 density waves on your star and superpose those. And
right, so it's a little bit different in the sense that there you don't have this sharp distinction between mismatched regions and non-mismatched regions. It's more like a continuous thing of like there's some regions where there's very little mismatch and some regions where there's a very high mismatch.
Yeah, right.
But it's still true in that case that, you know, the degree of mismatchedness becomes less as you make the size of these translation vectors larger.
Yeah, you know, there's this claim in the Moiré graphene literature that when you make the Moiré structure there, that the system is actually independent of origin shifts if you go to this continuum limit, where it's the analog to what you would be doing here with just plane waves. So I'm just wondering.
So that's true for like small twist angles, although
yeah.
It's not really what I'm talking about here. I mean,
right.
Here I want to consider something that is maybe not just like weak. That's sort of a weakly incommensurate case where you have 2 things which are very close together. Here I want to consider like the strongly incommensurate case. So that's a bit different from what's going on there.
Yeah, got it. Thank you.
So I have a quick question. Is this equivalent? Hi. Is this equivalent to say that I don't see Dominic now, but I see Eugene. see Eugene. It's equivalent to replace the quasi-crystal by some high commensurate version of it, essentially by a partial fraction decomposition of finite depth.
Well, so yeah, I mean, you can do that. It doesn't really.
It would be like essentially these commensurations every once in a while, like domain walls in that structure that will give you the full quasi-crystal. Is that what these pictures mean? Because this looks like a problem that is locally commensurate. And then every once in a while, you have some defect. And then you go into some other region. As you say, there are large chunks which essentially look as if they were translation invariant.
Yeah, it may be possible to think about it in that way. I haven't really thought about that kind of picture. At the end of the day, it's the.
This is Macmillan's picture of an incommensurate charge density wave as being locally commensurate with these commensurations, essentially. That will give you the incommensurate structure. So it's not a plane wave. It in fact has an infinite number of harmonics in that language.
Yes, I mean, yeah.
What Jane wanted, but in a sense.
That may be a way to think about it. But at the end of the day, it's the incommensurateness that is going to be important for what I'm going to say. So eventually you will need to reckon with vectors actually a quasi-crystal, at long scales.
No, I understand, but isn't that essentially what these fuzzy regions are? Essentially, like called domain walls between locally commensurate regions. Is that incorrect to think about it this way?
I don't know. I guess I'd have to think about that.
No, it's definitely one way of thinking about it. The perfect quasi-crystal, which lacks periodicity, is quasi-periodic. So this is a perfectly ordered structure. So the long-range order is exhibited by these Bragg peaks that Dominic showed. And if you take a continued fraction and chop it off at a finite depth, then you get a periodic approximant of the quasicrystal. So this one way of approaching a quasicrystal is by a sequence of these periodic approximants where the unit cell becomes larger and larger according to the infinite fraction description of the irrational number. So I think what everyone was saying is quite correct in terms of looking at the quasicrystal in different ways.
Yeah, okay, thanks.
And I wouldn't use the terms defects because these are not defects. Even these grayed out areas are perfectly ordered in the long range order sense of crystallinity. So
yeah, so the only reason they look like defects here is because I superimposed the quasi-crystalline.
But if you look at their autocorrelations in space, you'll see that they're perfectly ordered.
Yeah, originally before I did that superposition, it looks, there's certainly no defects anywhere.
Exactly.
So in any case, the important thing is that we have this kind of quasi-symmetry, which is the word I'm using to describe this non-trivial spatial structure that a quasi-crystal has.
So what you're calling quasi-symmetry is in fact the quasi-periodicity of the quasi-crystal.
Yeah, that's correct. I use the word symmetry because I want to try to explain why it's like kind of like a symmetry in terms of protecting topological phases. But yes, I just mean the quasi-periodic structure.
This is what replaces the periodicity of a periodic crystal. So the quasi-crystal is in fact a quasi-periodic crystal. It is a crystal. A quasi-crystal is a crystal in the sense that it has perfect long-range order, no defects, unless you introduce defects, of course, into it, like in a periodic crystal. And this is just the nature of the quasi-periodicity, is that there is no periodicity, but what you're describing here is in fact the outcome of the fact that it is quasi-periodic.
Yes.
And what you're going to show us, which is something I know nothing about, is how quasi-periodicity protects the topology.
Yes, right.
Thank you.
Yeah, so just to emphasize, when I say quasi-symmetry, I don't mean approximate symmetry. I mean, the crystals have an exact translation symmetry. Quasi-crystals have some exact structure. It's not quite a translation symmetry, which is why I call it quasi-symmetry, but it's not an approximate symmetry. It's whatever the structure is, it's an exact structure, which I think we already talked about before. And so the question is, can a translation quasi-symmetry protect topological phases? SBT stands for symmetry protect topological, if you didn't remember. So can the translation quasi-symmetry protect topological phases? And so the answer will be yes. That's kind of the point of my talk. So in order to show why that's the case, first let's consider other kinds of topological phases. So generally, so here I'm going to forget about translation symmetry or whatever, and just think about internal symmetries. Like we can think about something like U1, charge conservation symmetry, and how do you protect topological phases using that symmetry? And so the way to think of it in terms of quantized responses. So for example, if you have a U1 symmetry, you can couple to a background gauge field for that symmetry, which basically is like a electromagnetic field where you just treat it as a background. Then because the Hamiltonian that describes the system is gapped, you can actually integrate the original system out, and you're just left with a topological term or an action for the background gauge field that you couple to. And so, for example, if you're in two spatial dimensions, or 2+1 space-time, which people sometimes use that convention, then you can have a topological term which looks like this. So this is a Chern-Simons term. And so the coefficient of a Chern-Simons term is actually quantized by gauge invariance. And the physical interpretation of this coefficient is the whole conductance of the system. So it has to be an integer. You have an integer quantized whole conductance. And so this is how you classify topological phases of U1 symmetry in two spatial dimensions in terms of their quantized whole conductance, which can be described by this topological term. Now, if you want to talk about crystalline symmetries, let's not even talk about quasi-crystals yet, but just talk about crystals. And these are things that are protected by spatial symmetries, like translation symmetry or rotational symmetry. And so if you want to couple to a background gauge field for these things, you need to explain what it means to gauge spatial symmetries. So this is what we tried to do in this paper that I wrote a few years back. Well, I think we did it successfully, actually. And then see also some more recent work from other people. But an undesirable feature of this work, although I think it does let you give a classification of topological phases with crystalline symmetries, it's very formal. It's kind of hard to interpret physically what's going on. So it's not totally satisfactory from a physical standpoint, even though mathematically I do think it gives you the correct classification. And another problem with this approach is that it's very far from obvious how to generalize to quasi-crystals, because quasi-crystals don't even have symmetries. So what would you even gauge? So in this talk, I want to describe an alternative approach, which is both much more physical, I think, and also very much clearer how to generalize to quasi-crystals. So the idea is instead of considering about gauge fields, you just think about phonons. So if you have a solid and it has some crystal structure, you know that that's obtained by spontaneously breaking continuous translation symmetry. Therefore, there must be Goldstone modes associated with that spontaneous symmetry breaking, which is what we call the phonons. And so there's some elasticity theory of a system, which basically describes the low energy phonon excitations of the system. So where you take the original crystal lattice and just, allow it to be deformed in some one wavelength way, and then there's some dynamics of these excitations. That's what we mean by elasticity theory. And then we can talk about quantized topological terms that appear in the elasticity theory of the system. And so that's what I want to argue is a very good way to think about the crystalline topological phases protected by crystalline symmetries, is that you classify them by the manifestation of this topology in the elasticity theory of the system. And so, for example, if you consider a topological phase protected by translation symmetry in one spatial dimension, what we know is that such topological phases are classified by integers. And the interpretation of integer is very simple. It's just the charge per unit cell. So there's some result of the charge per unit cell in one dimension has to be an integer. That's the so-called Lieb-Schultz-Mattis theorem. And then for which integer it is, how many charges you have per unit cell of the system is going to be classified with distinct phases of matter. And so, sorry, what am I saying? So now I want to tell you how to think about this in terms of the elasticity theory. But first, I want to think about what does the elasticity theory of this system look like. So here I'm actually technically you cannot spontaneously break translation symmetry in one spatial dimension because of the Merman-Wagner term. But I'm not going to worry about that for this talk because it's not really the main point I want to make. So let's just forget about Merman-Wagner theorem and let's just assume that we have a system in one spatial dimension that spontaneously breaks continuous translation symmetry down to a discrete lattice subgroup. So you get some spontaneously formed periodicity as you see in this picture and with some unit cell. So you select out, even though you originally have continuous translation symmetry, the nature of spontaneous symmetry breaking is you select out a particular crystal structure. The point is that even though you have one ground state that looks like this, you can, because you originally had continuous translation symmetry, you can displace the ground state however you like. And that also forms a new ground state with the same energy. So generally when you have spontaneous symmetry breaking, you get a whole manifold of potential ground states labeled by the order parameter, and then you just, the spontaneous symmetry breaking selects out one of these ground states at random. So the point is that the order parameter that labels these potential ground states, in this case, you should think about it, lives in on the circle. So the order parameter is basically the displacement. The order parameter is basically this displacement, so it's how much you've displaced the crystal. And the reason it lives on the circle is because the order parameter is actually periodic, because if you translate by one unit cell, you get back to the same state. So that's why we identify the order parameter 0 and 2 pi, for example. So the order parameter really lives on the circle now. So now if you want to consider the low energy phonon excitations or the low energy elastic modes, that's where you allow this order parameter, which originally was just some static field labeling the ground states, but now you allow it to be slowly varying as a function of space and time. And now we can also imagine we couple to a background gauge field for the U1 symmetry described by a vector potential. And now we can write down an action for the phonons that includes, so there's some kinetic term which describes just the dynamics of these phonons. I won't worry too much about that in this talk because it's not important for what I want to say. But then you can also write down this topological term. So the topological term involves this background gauge field and the order parameter fields, and it's actually topological. It doesn't involve a metric of a system, so you can do any reparameterization of space-time, and the term is left invariant. And this topological term is actually gauge invariant when you make gauge transformations of a gauge field. Maybe it's not totally obvious here because I've written an A, and A is not gauge invariant. If it was just in terms of expressed in terms of a field strength tensor, which is dA, then it would obviously be gauge invariant manifestly. This one is not manifestly gauge invariant, but it actually is gauge invariant because of some global reasons. But that's true only if you make this coefficient quantized to be an integer. So this quantized coefficient is actually the same as the topological invariant that I discussed previously. It's the charge per unit cell.
So can I ask you a question? You're treating the crystal as if it were charged particles here to do this, right? Because you're charging this relative to this electromagnetic field, presumably. So this is the anomaly term that you will write in 1 + 1 dimensions is precisely this topological term that you write. But that's usually the axial anomaly in the usual expression, in the usual form.
Well, this one is not quite the...
It's actually the, yeah, that's what the axial anomaly looks like. In a one-dimensional, system fermions, it's a term like this.
No, but what would the theta be in that case?
Theta is the phase associated with the continuous chiral symmetry.
Okay, yeah. So okay, yeah, there may be some analogy. I mean, here it's
exactly this term.
Yeah, the term maybe looks the same. Here, the interpretation maybe is different because it's fading now as a phonon.
But I don't know what the vector potential in this case means. These are neutral particles.
No, these are not neutral particles. I mean, I assume that we have some U1 symmetry. So, and I want that U1 symmetry not to be trivial. So you wouldn't want to be just neutral particles. You would want to...
Okay, so this is actually the analog. Okay, in an electronic system, this U1 symmetry is the chiral symmetry associated with the rigid translation of the structure.
No, the U1 is not chiral symmetry. The U1 would just be the total charge, so like the non-chiral charge.
Yes, that's why it doesn't couple to the. That's why it couples this way, is because it is the chiral symmetry that you're doing here. It's exactly what is a gamma 5 transformation that you're making. So this is, so I'm not entirely sure if in a convention, I mean, you're saying simply because it's a crystal that you can slide in free space, it doesn't mean that it's charged under a vector potential. It's simply that free space is free, it's homogeneous, right?
Well, so the order, I mean, the existence of an order parameter obviously doesn't depend on charge, but the topological term will be present only if only if you have some charge degrees of freedom. Otherwise, the coefficient would just be 0.
The question is, what is the physical meaning of the vector potential? It's not the electromagnetic vector potential.
It is the electromagnetic vector potential.
And these things have to be charged, and they are not.
Well, I don't know why you say they're not. I haven't even given you a Hamiltonian yet, so I mean, you don't know if they're charged.
You're looking at the crystal, okay? In a crystal, the atoms are neutral.
Oh, okay. I mean, okay. It depends which charge you're talking about. I mean, okay, that's a good point. So it's not really the electromagnetic field. It would be like an electromagnetic field that couples only to the electrons and not to the atoms, for example, or only to the atoms and not the electrons. So again, in that sense, it's not really the real electromagnetic field, but because we assume that the U1 symmetry,
So then it's essentially, it's like the electron gas in one dimension, is whether or not you have a modulated structure which you can, it's like a density wave you're looking at now. Okay, well, look, maybe you should continue, but I'm confused about the meaning of, I like the symbols, I like the expression, I try to understand the physics associated with this and what assumptions are being made. So,
well, so you can imagine a very simple case, which is just a trivial atomic insulator where each unit cell contains one atom, and that atom has an electron tightly bound to the atom. But we take the U1 to be generated by just the number of electrons, not the total charge, just the number of electrons. So you have one electron per unit cell. So that electron is charged under the U1 by definition because its number of U1 is number of electrons. So that's the simplest case. Does that make sense?
that makes sense, but by treating the electrons as separate from the atoms, what you're doing is essentially looking at the conduction electrons of a crystal. Okay. And you're saying, well, you may have an integer number of them, which will be the commensurate case, I suppose. But if
yeah, well, we'll get to the incommensurate case later, but
right.
But yeah, so the commensurate case, you just have an integer number per.
I mean, if you have that picture, then certainly the conduction electrons coupled with electromagnetic field. There is no question about it. Okay, so. But I don't know to what extent I can blindly apply this just to a crystal made of neutral atoms, which are, you know, have some cohesive forces that keep them together. And
well, it's just a question of how you define this U1 symmetry. You can define the U1 symmetry to be the number of atoms, if you want, rather than the number of electrons. So then atoms are neutral under whatever the real electromagnetic field is, but they're charged under this U1 symmetry that we're defining. Because certainly number of atoms is a conserved quantity, usually. So we can have a global symmetry, U1 symmetry associated with that. And so they're charged under that.
I mean, you think that the vector potential is related to some geometric property of the space. In that case, you know, like metric. And then it's different. So,
well, vector potential is more like some fictitious thing.
yes,
well, I mean, this topological term has consequences, physical consequences, which I'm about to get to. But the vector potential is more like some fictitious device that we introduced to help understand the system, because you can't really couple to a vector potential for these symmetries usually.
Okay, please go on. I shouldn't interrupt you as much. Sorry.
No interruptions are good. But so one thing you can do with this topological term is you can compute the charge density of the system, right? Because the charge density is going to be the functional derivative of the action respect to the time component of the gauge field, ds dA naught. So if you do that from this topological term, you'll see the charge density is proportional to the dx theta, with its coefficient nu. So that makes sense. If you imagine that you build your system up and you have some charge nu per unit cell. Now, as phonons go through the system, they compress the unit cell or expand the unit cell. So the charge in each unit cell stays the same, but the size of the unit cell is fluctuating, which is what this dx theta tells you. If you have a non-trivial dx theta, it means that it means that you have some stress in the system, some strain rather, and the charge of the size of the unit cell is expanding and contracting. And so as the unit cell expands and contracts, you get some, you're changing the charge density of the system, because if you have one charge per unit cell, you expand and contract, you change the charge density of the system. So this is precisely the formula that you would expect for a system with one charge, or rather charge nu per unit cell. So the charge is coupled to the phonons, and that's what this topological term describes. So now if we move on to quasicrystals, you have to address the question of what is the order parameter of a quasicrystal. So you might have guessed that the order parameter is just lives in R, so it's just a real valued chain. Because remember, so for a 1D crystal, you have the order parameter field, which is the displacement field. But then I said it was periodic because of the residual lattice translation symmetry. makes the order parameter be periodic. But a quasi-crystal does not have residual lattice translation symmetry. There's no translation symmetries left after you've spontaneously broken. So you might say that therefore, to go from a crystal to quasi-crystal, you should just remove this periodicity constraint on the order parameter, which is living R. But actually, that's not really the right way to think about it, because you're not taking into account this quasi-symmetry structure. If you really had a disordered system, maybe this would be the right description of the order parameter. But for a quasi-crystal, you're not really taking into account the quasi-periodicity if you just try to make the order parameter live in R. Turns out the right way to do it is that the order parameter should be thought of as living on a d-dimensional torus for some capital D greater than 1. So here's a picture. So here's the case where you imagine capital D equals 2. So this is supposed to be a torus. So you imagine that this edge is identified with this edge, and similarly vertically, so that it would wrap into a torus. And so the order parameter lives on this two-dimensional torus. Now continuous translation operator still has to act on this order parameter, because you act with continuous translation operator on a ground state, you get some other ground state. So then there needs to be some action on the order parameter space that labels the ground states. So the action basically looks like this. If you start with some particular order parameter theta naught, and then you translate, you act with continuous translations, it moves along some direction in a torus. But for a quasi-crystal, actually moves in some incommensurate direction, as a consequence of which, if you keep translating and translating and translating, you never come back exactly to the same point you start with. What happens instead is you actually densely fill this torus. So that's the manifestation of this quasi-symmetry structure, because you're densely filling the torus. So if you wait long enough, if you translate for long enough, eventually you come back nearly to the same order parameter, but not exactly back to the same order parameter. So that's this idea that for large enough translations, you almost have a translation symmetry, but not quite. If you actually came back to the same exact point, that's when you would have a translation symmetry. The order parameter lives in this two-dimensional space now. So as a consequence of this, there's two kinds of elastic modes. There's the phonons, which correspond to order parameter fluctuating parallel to these blue lines. And then there's also phasons that correspond to order parameter fluctuating in perpendicular to these lines. So there's like two quote-unquote polarizations, if you like, of elastic modes. And we call these phonons and phasons. So quasi-crystals actually have more elastic modes than a crystal does, because the order parameter lives on a high dimensional space. So it's a similar story for d spatial dimensions. So in d spatial dimensions, the crystals have an order parameter that lives on the d-dimensional torus, but quasi-crystals have an order parameter that lives on the capital D-dimensional torus, and capital D for a quasi-crystal would be greater than little d. So the elastic modes correspond to fluctuations of the order parameter that lives on this manifold. And that's the information we need to be able to write down the generalizations of these topological terms. So for a quasi-crystal, for a regular crystal, you had this topological term with the coefficient nu, to couple the A, the vector potential to this displacement order parameter. But now for a quasi-crystal, the order parameter now lives on the D torus. So you have, if you like, D fields, theta 1 to theta D. So as a consequence of this, there's actually a family of different topological terms you can write. So here I'm using implicit summation over this index I. And so you actually have capital D different quantized coefficients, nu1, comma, up to nu d. Each of them are quantized to be integers. So there's actually capital D independent topological invariants that you can have in these quasi-crystal systems. So the fact that you had this quasi-crystalline structure is actually giving you more independent phases of matter compared with the crystalline case.
Dominic, could I ask a quick question?
Yes.
The capital D, is this at all related to the statements that sometimes you could visualize a quasi-crystal as projection from a high dimensional space? So for instance, in practical terms, 3D quasi-crystals are known to be either projections from 5 or 6 dimensional space, it depends on the details. So what determines capital D here? Is that indeed what I just said, or D could be anything?
No, it is related to that, although you should be careful not to take these high dimensional pictures too seriously, in the sense that sometimes people just want to say, well, you take some quantum many-body state in high dimensions and you just project it to lower dimensions, and that's how you make these quasi-crystalline topological phases. It's not really a good picture because there's no notion of a quantum many-body state of projection. So, but in terms of, if you just forget about the quantum state and just consider, the spatial structure, then it's certainly true that you can get these quasi-crystals by projecting from a high dimensional space. So this capital D is essentially the dimension of that high dimensional space, with the caveat that it has to be kind of a minimal dimension. Like, so for example, of these Penrose towers, you can get them by projecting a 5-dimensional space, but actually you can also get them by projecting a 4-dimensional space. People don't often talk about that so much because a 4-dimensional projection has less nice symmetry properties in terms of the rotational symmetries. But actually, so you can get the towering by projecting from a 4-dimensional space. So this capital D has to be the minimal dimension, minimal superspace dimension.
So the technical term for this capital D is the rank of the structure. So again, we're talking about a quasi-periodic structure. The rank is the minimum number of, if in this case it's in 1 dimension, so this would be the minimum number of periodicities that are you cannot express one in terms of the others using integer or rational coefficients. So the rank is the minimum number that you need in order to span the whole spectrum, the structural spectrum, not the energy spectrum, the diffraction pattern, using integer linear combinations.
Yeah, so that's exactly right. Yeah.
Dominic, and just to clarify, are the cetas taking values, are they compact variables? Should I think of them as phases?
Yeah, they're compact because they live on the torus. So it's just some component of the coordinate on the torus. So they would be compact as you go around the torus, comes back to the same.
Well, in that sense, I understand, but are they, is the dimension of the torus, so should I think of it as a phase space that's canonically conjugate to translation? So should I think of theta taking values, 2 torus whose length is 2 pi, just a d-dimensional realization?
Not sure if I understand the question. I mean,
so in one-dimensional, so maybe I'll step back. In one-dimensional analogy, the theta really played a role of like a quasi-momentum.
No, theta is not a quasi-momentum. Theta is, in a crystal, if you reduce to the crystalline case, which is where you set capital D equals 1, theta would be the displacement. So it's not actually, it's definitely not momentum. It's actually in some sense conjugate to momentum.
I see. Okay. Thanks.
Right. So you have these capital D independent integer invariants. So each one of these, each combination of these integer, so each assignment nu 1 to nu D assigns some integers. That's this different topological phase. So let me move on to a general classification. Hopefully it's not getting too formal, but I just want to remind you, if you have crystals protected by translation symmetry, it's topological phase protected by translation symmetry in a crystal, remind you like with a general classification, and I'll extend it to quasi-crystals. So it looks like this. So D choose, this is the binomial coefficient, D choose K. So you have K copies of this QK, and QK is a classification of strong topological phases, strong SPTs. So these are SPTs protected, topological phases protected by lattice translation. Sorry, topological phases that don't require translation symmetries protect them in K spatial dimensions. And so to get to a total classification of translation protected phases in D dimensions, you sum from K to 0 to D. So all the low dimensional strong SPTs enter into the classification. So the physical interpretation of that is, well, let's consider, for example, the case D equals 2. So you have total classification is Q2, which is just for the phases that don't require translation symmetry. You have 2 copies of Q1. And this is because you can take one-dimensional topological phases and stack them to get a 2-dimensional topological phase protected by translation symmetry. So this is kind of like a weak topological integrator that I mentioned before. But there's 2 independent ways that you can stack them. So you can stack them horizontally or vertically. So that's why there's 2 independent invariants you can choose. That's Q1. That's why I have Q1 plus Q1. And finally, there's Q0, which is the topological phases in 0 dimensions. That's basically just charges in 0 dimensions. And then you can stack these in 2 dimensions, and that gives you a topological phase protected by translation symmetry. So that's the interpretation of this general classification for the G equals 2 case. And now I want to say how this gets generalized to quasi-crystals. So quasi-crystals, you get a similar formula. Here you actually sum from k equals 0 to capital D. So capital D, remember this rank number that we talked about. It's the dimension of the torus that the order family lives in. Whereas little d is just the physical spatial dimension. And so you sum from k equals 0 to capital D, you get a formula like this. And so to interpret this formula, let's consider, for example, the case where a little d equals 2, capital D equals 4. So this describes, for example, the Aman-Bin-Catalan that I drew earlier in the talk would have these numbers. And so here you get, so you have the strong SPTs, so the phases that don't require any spatial structure to protect them, so that's as before. Then you get these weak topological phases, which are based on the classification of low dimensional topological phases. But you actually get more of them than in the crystalline case, because in the crystalline case, you just had Q1 and two Q1s. But here you have 4 Q1s and 6 Q0s. And then there's also these Q minus 1, Q minus 2, but I will get to that later. First, I want to tell you how to interpret these weak topological invariants and the fact that you have more of them in the crystalline case. So to do this, it's helpful to use this tiling picture that I introduced before. So here is the Aman-Bin-Catalan that I drew before, but I removed the colors now. So this tiling is actually built from 6 fundamental prototiles. So here I've drawn the 6. So any of the tiles that appears in this tiling of space can be related by translations back to one of these 6 prototiles. Here I'm not imposing any point group symmetry. That's why I consider like this I12 is different from I23. I mean, if you impose a rotational symmetry, they would be related, but I'm not imposing such a symmetry, so I take them to be independent. So now the point is that, so let's understand these topological phases that are just related to the classification of 0-dimensional topological phases. So the idea is, so if I had a crystal, then in each unit cell, I could put a charge. I could put some number of charges in that unit cell, and then the total charge per unit cell would classify the possible 2-dimensional phases protected by translation symmetry. Here we have a similar picture, but instead of having a charge in each unit cell, you put a charge in each tile. But each tile can contain a different amount of charge if you want. So each of these colored dots represents some number you can choose independently, how many charges you want to put in each tile. So then you fill space with these charges. Whenever you see a given tile, you relate it back to a given prototile, and then you put that amount of charge on the tile. So you can have charge 1 on this tile, charge 2, you can have some, you can have charge 1 here, charge 3 here, charge 5 here, or whatever assignment of integers you want, you can put that amount of charge on each tile, and then you make some state. And so by building a state in this way, you get basically a representative state for each possible phase in the classification. So similarly, for the one-dimensional, similarly for the chart, so we're always working here in 2 spatial dimensions, but we have phases that are related to the classification of topological phases in low dimensional. So here is where it was related to 0-dimensional topological phases. And then there's also the case where you're related to 1-dimensional topological phases. So here, instead of looking at the tiles, you look at the edges of the tiles. And it turns out there's actually 4 different kinds of edges. For each edge, you can put a 1-dimensional topological phase on the dual lattice so that it pierces this edge. And so again, we have different colors because you can choose this 1-dimensional topological phases independently for each edge. And so you make a two-dimensional state by building it out of these one-dimensional topological phases. But each color represents a 1D topological invariant you can choose independently. So for the two-dimensional classification, you get these 4 independent invariants that you can choose. So that's basically the physical picture of these weak topological phases. So even though there's no translation symmetry, which is normally how we think about weak topological phases arising, you still have analogues of the weak topological phases that are protected by this quasi-crystal structure. And in fact, you have more of them because you can choose all of these topological invariants independently. Okay, so that's the physical picture of these phases. Well, is there any questions on that? I should probably wrap up soon, but this is a good point to ask for questions on this physical picture.
I have a quick question. So if I understand correctly, so I understand that these phases are similar to the weak topological oscillators, and so far everything makes sense. But I'm wondering if you know whether there is an associated bulk edge correspondence for these.
Yeah, that's a really good question. There probably is, but we haven't. It's a little bit tricky question to think about. We haven't really worked it out yet. So for the crystalline case, if you have and for a crystalline case, the bulk edge correspondence for phases protected by translation symmetry is already a little bit tricky because the edge always breaks some translation symmetry. Nevertheless, you still have an edge that although it breaks some subset of translation symmetry, there's still some translation symmetry left. Like if you're in 2 dimensions, you can still translate maybe along the direction of the edge, and that translation symmetry would be preserved, and that might be enough to protect gapless edge states. So probably there's something similar here. It's just a question of what exactly is the property we want to demand for the edge, because you can't phrase it in terms of symmetry anymore. These systems don't have any translation symmetry to begin with. There's some property of the edge that may mean that the edge protects gapless edge states. But we haven't worked out exactly what the way to formulate that would be.
All right, thanks. That's clear.
Dominic, could I ask just to clarify, in a given subdimension, let's say the one that's shown here on the screen, then the possible values that take place in this group Q1 would be, in this example, 4 different configurations corresponding to orange, green, red, and blue color. Is that correct? As was, if I ask you, what is the invariant that classifies the one-dimensional substructures as written here, the Q1? Would there be 4 of them? Would it be Z4 valued?
Well, it depends so Q1 is a classification of topological phases in one spatial dimension without any translation symmetry. So it depends exactly what context you're talking about. For example, if you're talking about topological superconductors, we know that there's a Z2 classification of let's say topological superconductors in class D, so you don't impose any time reversal symmetry or anything like that. So then there would be a Z2 classification of one-dimensional topological superconductors. That's the Kitaev chain and the trivial chain. So then Q1 would be Z2, so it would be Z2 to the 4th. But it depends what the classification is in one dimension. That depends on whether you're talking about bosonic or fermionic systems and what the symmetry class is.
So in other words, if you start with non-interacting Adlan-Zornbauer classes, it may be that Q1 is trivial, right? For instance, you might be in such a state. Yeah,
so because we're always talking about interacting systems here, so you should start with whatever the interacting classification is, which may be different from the outline Zornbauer classification.
But is it conceivable that one of those Qs would actually be trivial? As in, it doesn't matter,
Yeah, depending on what internal symmetries you impose, and it certainly may happen that Q1 is trivial. So in that case, there wouldn't be no contribution. There would be no non-trivial invariance, at least not associated with this term.
Makes sense. And is there any general comment you could make if you start with a bosonic system with no other symmetries present? Only this quasi-translational symmetry of the quasi-crystal, nothing else. No particle hole, no time reversal. Is there any statement you could make about what Q2, Q1, Q0, and so on, what those values are?
Yeah, so I mean, that's the question of the classification, just the classification of phases without symmetry. And here we're kind of talking about the so-called short-range entangled states, although you can talk about the long-range entangled states, but that's different from the classification I'm talking about here. So the short-range entangled states, the answer is, as far as we know, Q0, 0, Q1, 0, Q2, Z. And that's the so-called Kitaev E8 state. Q3 probably is trivial, and then, okay, maybe that's as high as we need to go. So the only non-trivial one would be Q2, which is the Kitaev E8 state. It has a Z classification. Does that answer the question?
Yes, it does. Thanks.
Sorry, what are Q minus 1 and Q minus 2?
Okay, that's what I was going to get to. Although I'm a bit short on time, but okay, let me jump to that now. So the definition of the QKs is a classification of strong SPTs, or strong topological phases in K spatial dimensions. So by this token, you would say these terms don't make no sense. How can you have topological phases in negative spatial dimension? Okay, so I don't want to take the language too seriously, but it does turn out that you have to include these terms in order to get the correct classification of the translation of the quasi-crystal protected topological phases. You have these additional terms that are on top of these weak topological invariants. And this is actually a new phenomenon for quasi-crystals. There's no analog of this in crystals. So these are describing intrinsically quasi-crystalline topological phases that really have no analog at all in crystalline systems. So the weak topological phases, they're kind of analogous to the case in the crystalline systems, but with a richer classification. But these intrinsically quasi-crystalline phases really are totally new. So that's an interesting observation. So it turns out, this is just something I'm telling you for the moment. For a system with time reversal symmetry, you should set Q minus 1 to be Z2, Q minus 2 to be 0. For a system without time reversal symmetry, you should take Q minus 1 to be 0, Q minus 2 to be Z. Anyway, so the point is, the reason why these intrinsically quasi-crystalline phases exist is you can understand in terms of these topological terms that I talked about before. So there are topological terms you can write down that would correspond to these intrinsically quasi-crystalline phases. And so they look something like this. So this is, again, in the case of two spatial dimensions. So before I wrote down topological terms that couple the phonon field, or in this case, it's the phonon and phason field, the theta fields. Before I coupled that field to the vector potential, but this topological term actually doesn't couple to a vector potential, so it doesn't even require any U1 symmetry or anything like that. Anyway, you can always write such a topological term. It's basically a theta term for these theta fields. It measures some kind of winding number of these theta fields in space-time. You can always write down such a topological term. So this theta ijk, some coefficients, some anti-symmetric tensor of coefficients. If you impose time reversal symmetry, it turns out this theta ijk is actually quantized to be 0 or pi. So that may remind you of things you've seen before in the theory of topological insulators, for example, but that's for electromagnetic fields. But here we have this theta term for these fields. There's too many different thetas here, but we have these theta fields, and we can write down a topological term that has these quantized coefficients. So because this topological term is in theory can be there, it means that it must correspond to some, if this topological term is present, it corresponds to some non-trivial topological phase that's protected by the quasi-crystallinity. I wish I could tell you more about the physical properties that this phase would have. Unfortunately, we haven't really worked out what the physical consequence of this topological term would be, but in any case, these phases must exist. And so that's with time reversal symmetry. Without time reversal symmetry, there's actually a different kind of action you can write down. So so-called Westing-Minor type action, where you extend the theta fields into a high dimensional space, and the original spacetime is on the boundary. And then you write the action is the integral of a Lagrangian, but in the high dimensional space. That's the usual story for Westing-Minor terms. And actually, but the action doesn't depend on the extension into the high dimensional space. Because you chose this coefficient to be an integer, it ensures that the action doesn't depend on the extension to the high dimensional space. So that's a Westing-Minor type actions. And so this is responsible for this Z classification. And again, I don't really understand the physical implications of this term. Certainly it will affect the dynamics of the phonons and phasons. We know that Western terms do that. But exactly what happens, I'm not sure. But in any case, these intrinsically quasi-crystalline topological phases exist, and they need to be understood better what they would imply physically. So this is related to this higher dimensional Berry's phase that Kapustin and Spodinenko discussed recently, but that work itself is kind of formal, so I haven't managed to extract much physical from it. Okay, I don't know how enlightening this was, but this was telling you that there are these intrinsically quasi-crystalline topological phases. So I don't want to take too much time, so maybe I can just skip over. There are different applications you can do for these topological terms. Here I'm coming back to the weak in topological phases rather than these intrinsically quasi-crystalline phases that we don't understand so well. But for weak topological phases, there are various interesting applications. Such as, for example, you can generalize the Lieb-Schultz-Mattis theorem to quasi-crystals. You can talk about introducing dislocations and think about the mobility constraint on these dislocations. They can move only in certain directions, and you can explain that as a consequence of this topological term and by imposing charge conservation symmetry. And there's a general classification that we can do, but let me skip over that. So we can give a classification of quasi-crystalline topological phases very generally, incorporating both this translation quasi-symmetry and also point group symmetries. So there's a very general theory that you can have. Yeah, but I should stop there because I'm already been talking for an hour. Anyway, it was great that we had so many questions during the talk, but if there are further questions, I can answer them now.
First of all, thank you very much for the presentation. I have speaking about these interesting quasi-crystalline only terms. Do you have an idea of the kind of microscopic Hamiltonian where these might arise in the low energy limit?
Well, yes and no. I can write down some kind of very weird toy models that would give rise to them, but I mean, they're certainly not realistic. I mean, in terms of identifying, what kind of material you might expect these terms to appear in.
No, right? Yeah, that's all right. Yes, yes, but still okay. But you're saying that you do know in which kind of hopping models these terms would arise.
Maybe even a hopping model is a bit of a stretch, but it's more like you write down some Hamiltonian, you assume that there's some quasi-crystalline order parameter, like some charge density wave or something. And then we write down a ground state that depends on this order parameter in a certain way. So maybe it's not even quite at the level of a hopping model, but it's some way of taking some quasi-crystalline order and assuming that the local degrees of freedom coupled to that order parameter in a particular way, it would give you this topological term.
All right, thanks.
So in the crystalline case, one can classify topological defects like dislocations and so on.
Right.
Is there an analog of that here? And can you classify what their topological charges are, if any?
Yes.
Yes. So, I mean, I did mention, I guess I skipped over this, but there's some interesting properties of dislocations in quasi-crystals. So, yeah, so dislocations turns out that they still exist in quasi-crystals. So instead of the Berger's vector, you can think about the dislocations just as vortices of these theta fields that I introduced. So there's actually, like for example, the classification of dislocations in a crystal is like z squared. Say if you're in two spatial dimensions, and for a quasi-crystal with capital D equals 4, it's like z to the 4th. So actually, the quasi-crystals have more the dislocations are more independent indices for the dislocations. And then you can talk about like, does the dislocation carry gapless edge mode, protected gapless mode, which is something that often happens in these weak topological phases. Yeah, so you can extract all that information from the general theory that we have.